Hello, I am Sreja MR. I am working as lecturer in Department of Polymer Technology, Karnataka Polytechnic, Mangalore. I am interested by Department of Collegiate and Technical Education, the subject of Elements of Chemical Engineering, third semester. Today I am going to take Fluid Flow Measuring Devices, Unit 2, Session 1. Topic of today's session are flow measuring devices. We are going to handle venturimeter, orifice meter and then multiple choice questions. Venturimeter principle. The basic principle on which a venturimeter works is that by reducing the cross-sectional area of the flow passage, a pressure difference is created, and the measurement of pressure difference enables the estimation of discharge or flow rate to a pipe. So when venturimeter is used to measuring flow, here the flow to a venturimeter is varied. We have a cylindrical conical section, throat, divergent section. We are varying the flow of the liquid so that we can measure a pressure difference and then we can find the flow rate through the tube. This is a diagram of venturimeter. Here we can see there is an inlet section, a converging section, throat and then a diverging section. Here the initial section has the same diameter of that of the pipe to which it is connected. Then there is a section of high pressure tap, then a converging section, throat. The converging section is an angle of 15 to 20 degree. Throat, here low pressure tap is placed and high pressure and low pressure tap. There is a manometer placed to find the pressure difference, pressure head. So there is a diverging section. So when fluid flows, it has high pressure over here. In the converging section, the fluid gets accelerated. Then at the throat, the fluid flows with maximum highest velocity. At this point, when the velocity is highest, the pressure will be lowest. So this area is a low pressure area, and then afterwards the fluid comes back to the original state in the diverging section. So it consists of a converging section, throat and a diverging section. Converging section is at an angle of 15 to 20 degree cone angle, and diverging section has an angle of 5 to 7 degree. Now we come to construction. As explained in the figure, it has an inlet section, a convergent cone section. A converging cone angle is 15 to 20 degree. The length of the converging section is 2.7 d minus dt. D is the pipe diameter and dt is the throat diameter. D is the pipe diameter and dt is the throat diameter. Cylindrical throat. The diameter of the throat is half the pipe diameter. So in the throat, the diameter of the throat is half the pipe diameter where the fluid is accelerated. Now we come to construction of venturimeter. In venturimeter, a diverging section is there. It has a diverging cone angle of 5 to 7 degree. Now working of venturimeter. A venturimeter of known coefficient is installed in the pipeline and pressure taps are connected to the pressure measuring device. So, for knowing the flow rate of the pipe, we connect the venturimeter to the pipeline, and then by using pressure tabs we measure, using a manometer we measure the pressure of the system, of the fluid. An increase in velocity at the throat decreases the pressure, and this is measured using manometer or pressure gauge. There we are increasing and decreasing the fluid flow. At the convergence section, fluid is accelerated. The throat, it again attains maximum acceleration for the fluid, and again in the divergence section it is deaccelerated. So by increasing the flow velocity at the throat, pressure difference can be calculated using manometer or other pressure gauges. So we are coming to the derivation part. We are considering a venturimeter fitted in a horizontal pipe through which fluid is flowing. So we are considering a horizontal pipe. We are assuming the fluid is flowing through the pipe. So we are taking two sections. Let D1 be the diameter, P1 the pressure, V1 the velocity, and A1 be the area of section of fluid at the inlet section 1. And A1 is termed as the formula pi by 4 D1 square. So for the initial section 1 or the high pressure section, D1 is the diameter of the section, P1 the pressure, V1 velocity, and A1 the area of section of fluid. A1 equal to pi by 4 D1 square. Similarly, we are taking section 2, there P2, V2, D2 and E2 are the corresponding values. P2 the pressure, V2 the velocity, D2 the diameter, and E2 the area. Area will be pi by 4 D2 squared. We know in a constant flow pipe, two sections will have the equal energy. According to Bernoulli's equation, at 2 points, the total energy, that is pressure energy, kinetic energy plus potential energy, will be constant at any 2 points of a pipe. So P1 by rho g plus V1 squared by 2g plus C1 equal to P2 by rho g plus V2 squared by 2g plus C2. We know P1 by rho g is the pressure, P1 squared by 2g is kinetic energy, Z1 is potential energy. And this is the pressure, kinetic energy and potential energy for 2.2. As the pipe is horizontal, we are taking a horizontal pipe, so Z1 equal to Z2. It is the energy due to the height, due to Earth's magnetic field, or due to height. Z1 equal to Z2. Now coming to the next part. P1 by rho g plus V1 squared by 2g equal to P2 by rho g plus V2 squared by 2g. That potential energy is same, so that can be cancelled. Now this equation remains. This is CD, which is the coefficient of discharge of venturimeter. It varies from 0.96 to 0.98. The value is less than 1. Coming to the derivation, we have cancelled the potential energy part. Then again from the equation we can get P1 by rho g minus P2 by rho g equal to V2 squared by 2g. We can bring this term to the right hand side. It's V1 squared by 2g. Now P1 minus P2 by rho g is equal to V2 squared minus V1 squared by 2g. This is the difference at the section 1 and 2, and it is equal to H, or the pressure head. This is is the pressure head. That is, H can be written as V2 squared minus V1 squared by 2G. Now we are applying the continuity equation. That is, area into volume equal to A2 velocity is equal to A2 V2. That is, A1 is the area, V1 is the velocity. Now V1 equal to, we can bring A1 down, A2 V2 by A1. Then in H, we can substitute for V1. H equal to V2 squared minus V1 squared by 2G. In place of V1, we can substitute A2 V2 by A1. Now H equal to V2 squared by 2G, we can common take outside, 1 minus A2 by A1 squared. This can be written as V2 squared by 2G, A1 squared minus A2 squared by A1 squared. That is, V2 squared equal to A1 squared into 2GH all divided by this term we have to bring down, A1 squared minus A2 squared. We can obtain V2 as A1 into square root of 2GH by square root of A1 squared minus A2 squared. Then discharge Q equal to A2 V2. That is, A2 into A1 root of 2GH by root of A1 squared minus A2 squared. Then Q can be termed as A2 A1 root of 2GH by A1 squared minus A2 squared. This is the theoretical value, but actual discharge will be less. Then a coefficient of discharge CD comes into play. That is, this is theoretical discharge. Actual discharge, we have to multiply theoretical discharge into CD. CD is the coefficient of discharge. Next, we are coming to CD be the coefficient of discharge of venturimeter. The value is less than 1 and CD varies between 0.96 to 0.98. Let us see the advantage of venturimeter. So, advantage of venturimeter, it can be used in wide range of flow ranges. It has low pressure loss. It can be used for measurement of both compressible and incompressible fluids. Disadvantage of venturimeter. It is expensive and bulky. It occupies space. It's complex in construction. The ratio of tube diameter to pipe diameter cannot be changed. Not suitable for flow measurement of high viscous slurries. It may clog the system. So high viscous slurries cannot be used. It is very complex. And the ratio of tube to pipe diameter cannot be changed. Next is orifice meter. The principle of orifice meter. The basic principle on which an orifice meter works is that reducing the cross-sectional area of flow passage of fluid. On reducing the cross-sectional area of flow passage of the fluid is accelerated and a pressure difference is created, which helps to determine the discharge rate through the pipe. So, we are reducing the cross-sectional area of flow so that a pressure difference is created, and this helps to determine the discharge rate through a pipe. Orifice meter. So, in orifice meter, we have a orifice plate. It has a bevel angle of 30 to 45 degree. it is facing the downstream part. So we can see the flow of fluid. This is the pressure tap 1 and pressure tap 2 is fixed at the point where the velocity is, at this point the velocity is maximum, and hence there is low pressure created. The diameter of this plate has point, it is called the orifice. So the diameter of the orifice face can be changed. So there are two pressure taps, pressure 1 and 2. 2 is the low pressure tap and pressure 1 is the high pressure tap. By connecting the manometer to this, we can measure the pressure reading of the orifice meter, and from the pressure reading we can measure the flow rate. Here, when the fluid flows, an acceleration occurs to the fluid. As a result of this acceleration, high velocity is produced and a low pressure area is created. Orifice meter construction. So orifice meter consists of a flat circular plate with an accurately machined and drilled circular hole called orifice. It's a plate with a circular hole called orifice. The orifice plate is clamped between two pipe flanks with a beveled surface facing downstream. So for the orifice meter is clamped between two pipe flanks. Bevel surface will be facing downstream. Pressure taps are provided on the upstream side and downstream side of the orifice plate. On the downstream side orifice plate, pressure tap is provided. So pressure tap is provided two areas. One is high pressure area and another is low pressure area. The pressure difference is measured using a manometer. So here is the schematic diagram for the orifice meter. Here we can see pipe of diameter D. The orifice diameter is DO. Orifice plate which has a bevel angle. It is clamped in the pipe flanks. Then the fluid is flowing. It is accelerated in the orifice plate and at a point it attains maximum velocity. This point is called vena contracta diameter, and then it is deaccelerated. So at these 2 points, high pressure and low pressure area, a pressure drop across the orifice is noted, and this is termed as H. So it is another diagram. So we can see fluid is flowing. When it reaches the orifice plate, what happens? It gets accelerated, and CC is vena contracta, and then it deaccelerates. This is the flow pattern in an orifice meter. So now we are going to the derivation part. So according to Bernoulli's theorem, we are considering 2 points in the flow meter. Let D1 be the diameter, P1 pressure, V1 velocity, and A1 area of section of fluid at inlet section 1, and P2, V2 and A2 are the values at section 2. Applying Bernoulli's equation at section 1 and 2, we can get P1 by rho g plus V1 squared by 2g plus C1 equal to P2 by rho g plus V2 squared by 2g plus C2. As the pipe is horizontal, we can take Z1 and C2 as equal, and we can cancel them out. So the remaining ones we can write as P1 by rho g. We can put this term P2 by rho g to the left hand side is equal to V2 squared by 2g minus V1 squared by 2g. Here common rho g can be out, P1 minus P2. which is equal to V2 squared minus V1 squared by 2G. Here V1 minus P2 by rho G is H, taken as H. H is equal to V2 squared minus V1 squared by 2G. So here we have V2 squared minus V1 squared equal to 2GH. Then V2 is 2GH plus V1 squared. Then V2 squared is 2GH plus V1 squared. V2 is root of 2GH plus V1 squared. Now the discharge Q equal to A to V2. It is theoretical discharge is A2 into root of 2GH plus V1 square. Actual discharge, we are multiplying coefficient of discharge, then CD into A2 into root of 2GH plus V1 square. There is a slight shift in the formula, please. Sorry for that. Orifice meter. Advantage of orifice meter. It is simple in construction, easy to install and replace. It is relatively cheap. Ratio of orifice diameter to pipe diameter can be changed. Disadvantage of orifice meter. One is power loss. Second is loss of pressure in the instrument, and it cannot be used for slurries that may clog the orifice opening. Now differences between venturi meter and orifice meter. Venturi meter, we can see complex in construction. Orifice meter is simple in construction. Venturi meter occupies space. Orifice meter needs low space requirement. Venturi meter is expensive. Orifice meter is cheap. Venturi meter root of true to pipe diameter cannot be changed. Here ratio of orifice diameter to pipe diameter can be changed by installing new orifice plate. Pressure recovery is high, pressure recovery is less. Coefficient of discharge is 0.98, coefficient of discharge is 0.61. Coefficient of discharge can vary from 0.96 to 0.98. It has smaller power loss, it has larger power loss. Fluid orifice meter has larger power loss. Fluid is retarded gradually, fluid is retarded at once in an orifice meter. So now coming to multiple choice questions. How is the pressure difference measured in venturi meter? Using a piezometer, manometer, pressure gauge, orifice. So in this unit we learned about the manometer, or pressure gauge can also be used for calculating the pressure differences. Answer is manometer. Second one, the coefficient of discharge of venturi meter is CD is 0.96, 0.8, 0.6, 0.2, 0.4, 0.96, 0.8, 0.6, 0.4. The answer is 0.96. What is the converging cone angle of venturi meter? 5 to 10 degree, 15 to 20 degree, 45 to 50 degree, 20 to 25 degree. The converging cone angle of venturi meter. It is 15 to 20 degree. In the orifice meter, vena contracta is a point where dash is maximum. Area, velocity, pressure, temperature. So it is velocity is maximum. What is the cone angle of divergent section of venturimeter? It's the cone angle 5 to 10 degree, 15 to 20 degree, 5 to 7 degree, 20 to 25 degree. 5 to 7 degree is the answer. Thank you.